Alright class, today we are starting chapter 3, which is our main proofs chapter. We're starting out small today with conjectures and counterexamples. These are parts of proofs, these are things that are going to get us to where we need to be when we're writing our proofs. Our learning intention for the day is, I am learning how to make mathematical guesses based on patterns. Patterns are called conjectures. And how to test if they're always true by finding examples that prove them wrong, otherwise known as counterexamples. Hopefully by the end of this lesson, you'll be able to say that I can identify and differentiate between various types of statements, including simple and compound statements, and that I can identify and demonstrate an understanding of inductive reasoning, including those patterns and counterexamples, our conjectures and counterexamples. We're going to start out like we normally do, new chapters, with some vocab. What is a statement? A statement is a statement that is either true or false. This value, whether it's true or false, is called the truth value. And when we are writing a statement, it's represented using the letters P and Q. If there's more than two things being said, there may be an R in there as well. So again, could be Q, P could be Q, or R. So a simple statement that we could be talking about is something that we did last chapter. Supplementary angles have a sum of 180 degrees. Is that true or false? That'd be true. All right. Next we have a negation. A negation is the opposite truth value of that original statement. It is shown by the symbol. We've seen something like this before, a little squiggly. That means not P. That's that negation. So an example of not P would be supplementary angles do not have a sum of 180 degrees. Do not have a sum of 180 degrees, which we know that is false. A few more quick words to know. Conjunction. Statements joined by the word and. Written as P with an arrow pointing up, Q. And for a conjunction to be true, both statements must be true. So again, it's written as P and Q. P and Q. If conjunction was joined by the word and, then disjunction is a statement joined by the word or. This one is written with an arrow pointing down, and it's true when at least one statement is true. So again, this one is written P with a downwards arrow Q, so that's P or Q. Okay. So we're going to actually get into some of these a little bit, and we're going to see the difference between a conjunction, a disjunction, along with statements and negations. So let's go ahead and move down here a little bit. We're going to look at this shape. Use the statements to write each conjunction, then find the truth values and explain your reasonings. We'll get to that. Okay. So our first statement, statement P, says that the figure is a pentagon. Well, is this shape a pentagon? No, this is a square. So what is the truth value of this first statement? The figure is a pentagon. That is false. How about the second one? Q Q. The figure has 4 congruent sides. Well, that's true. And how do we know that? Because they have these little lines here that tell us that these are congruent. Finally, R, the figure has 4 right angles. That is true, and we know that because all of the angles have the right angle square. So if we look at this statement right here, P and R, what did we say for and? Both must be true. The figure is a pentagon, and the figure has 4 right angles. The statement R is true, and P is, well, we said P was false. So P and R is also false. Even though one of them's true, it's an and, so both have to be true. How about the second one down here? Not P and Q. The figure is a pentagon. The figure is not a pentagon, not. And the figure has 4 congruent sides. So it's a negation. That means not P is true. Q is true. So both P, not P, and Q are true. So not P and Q is also true. Okay. Hopefully that's making a little bit of sense here. We can, again, start to figure some things out here. For this next little set, we're looking at compound statements, and we're going to write them using the statements below. So let's get to it. This says P and R. So we can write the statement. There are 7 days in a week, and Halloween is on October 31st. Okay? So, let's find the truth values of both of these. P, there are 7 days in a week. Well, that's true. Is Halloween on October 31st? Yes, it is. So our truth statement for P and R, well, P is true and R is true. So if we look back up here, for and statements, both statements must be true, so this statement has a truth value of true. How about not Q or R? So Q is March has exactly 30 days, so not Q says March does not have exactly 30 days, or Halloween is on October 31st. What is our truth value? Well, Q's March has exactly 30 days. Well, we know that March has 31 days, so that's a false. But R's is not Q. So March does not have exactly 30 days. That is now a true statement. And then we have an or. R we already said was true. For an or, we only need one statement to be true. We have both of them being true, so this one's definitely a truth value of true. For this last one, we have not P or not Q, so our statement would be there are not 7 days in a week, or March does not have exactly 30 days. So what would our truth statement be? Well, there are not 7 days in a week. That's false. Or March does not have exactly 30 days. Well, we already had that one on there. That one's true. For an or, we only need one of them to be true. So that makes this one have a truth statement of true. We all following along still? We all good? Okay. So what I would want you to write down here in your summary, just real quick. We're going to look at the different possibilities for our and or statements. If we have a statement that says true and true, that has a truth value of true. What about true and false? Those could be switched. It could be false and true. That would also be false. What about false and false? Well, we need both of them to be true. Both of them are false, so that would be a false. What if we had the same statements, but now it's an or? True or true? Well, we only need one, so true. True or false? Well, we only need one, so true. False or false? Well, that's the only one for an or. That would be false. Let's keep on moving here. Looking at our second page of notes. And same success criteria, same learning intentions. Now we're taking a look at that word inductive reasoning. So we're figuring this part out up here. All right. What is inductive reasoning? Inductive reasoning is making a conclusion based on observations and patterns. This sounds pretty similar to stuff that you guys have done in science. This is an experiment of sorts. You're watching that observation. I think it's called either qualitative or quantitative reasoning in science. We just call it inductive because it's words. Math doesn't use words. Okay. And finally, conjecture. A conjecture is a concluding or finishing statement reached using inductive reasoning. So what you see here are 4 different sets of numbers that or letters that all have a specific way of getting to the next number. I'm going to do a couple of them, and then you're going to pause this video and you're going to do a couple of the others. Okay? So let's take a look at number 1. We've got 38, 31, 24, 17. Can you see how this is changing each time? Is there a pattern that's going on? How do you go from 38 to 31, and then 31 to 24, then 24 to 17? You figure it out yet? Well, I'm noticing that it goes down by 7 each time. So I'm going to take away 7 from 17, and I'm going to get 10. Then I'm going to do that again. I'm going to get 3. I'm going to get negative 4. I'm going to get negative 11. And I'm going to get negative 18. So the conjecture, what we're putting into words, is to get the next term in the sequence subtract 7 from the previous term. Okay. Let's take a look at the second one. 2, 5, 11, 23. Well, we can't say it's adding because to go from 2 to 3, it's plus 3. 5 to 11 is plus 6. 11 to 23 is 12. Oh, there's a little pattern there. It's multiplying by 2. The amount that it goes up each time. So that tells us there's going to be a times 2 somewhere in here. 2 times 2 is 4 plus 1. 5 times 2 is 10 plus 1. 11 times 2 is 22 plus 1. 23 times 2 plus 1 is 47. 47 times 2 plus 1 is 95. 95 times 2 plus 1 is 191. 191 plus, or times 2 plus 1 is 383. And 383 times 2 plus 1 is 767. So our conjecture, we don't have to write out the whole thing like this. If you see a little pattern like that, it's 2 times our previous number plus 1. Again, if you want to write that out, two times the previous number plus 1. Now, I want you to pause the video and see if you can't come up with the rest of these conjectures. I'm going to give you guys a little bit of time to do that as you pause this. All right, now that you've paused it, let's get back into this. We got 1, 4, 9, 16. These should look familiar. 1 is 1 squared. 4 is 2 squared. 3 squared. 4 squared. So then we have 5 squared, which is 25. 6 squared, which is 36. 7 squared, which is 49. 8 squared, which is 64. 9 squared, which is 81. So that makes our conjecture our number squared. Again, if you want to see that written out, our number squared. And finally, just because it's math, we're going to make it difficult and throw some letters in. A to D, D to G, G to J. Then it's going to go M, P, S, V, Y. Hopefully you got that. And we skip 2 letters. That's conjectures. Now let's take a look at the other side of it, of counterexamples. A counterexample is an example that shows a conjecture to be false. So our entire goal for this bottom section is to look at these statements and see if we can make it false, however it can be. Okay? So again, a counterexample is an example that shows a conjecture is false. So the sum, number 1, the sum of any 2 consecutive integers is always odd. So first we got to know the language. Consecutive. Well, consecutive just means one after the other. And integers have no decimals or anything like that. So that could be 1 plus 2. Well, that's 3. 2 plus 3. That's 5. 3 plus 4. That's 7. I think you're noticing a pattern here. Odd, odd, odd. It will always be odd So this is true. We don't have to show any more work for that since it is a true statement. All right, the second one. The product, so multiplication, of two numbers is always larger than either number. The product of two numbers is always larger than either number. Okay? So, we know we're multiplying. We know we're multiplying. Okay. Two numbers is always larger than either number. Can we show that it is not? Okay? Pick a number. Well, I'm going to say something like -4 times 8. What's -4 times 8? -32. Is -32 bigger, larger than 8? Is it larger than -4? No. What if we did something like 1/2 times 1/3? Well, that's 1/6. That's smaller than both of those. So we just came up with two counterexamples. All we needed was one to show that was false. All right, number 3. The product of two perfect squares is always a perfect square. So again, we got to know this is multiplication. Two perfect squares. So that could be something like 4 times 16. Well, what's 4 times 16? 64. How about 9 times, pick another one, doesn't really matter. We'll say 25. That's 225. You can keep trying these, but both of these are perfect squares. And I'm just going to tell you that that's true. It's perfect squares. So, true. All right, last two down here. If the area of a rectangle is 6 meters squared, then the dimensions must be 2 meters by 3 meters. So, can you draw another triangle, or can you think of another triangle that has an area of 6 meters squared that is not 2 by 3? Well, how do you find the area of a rectangle? You multiply length times width. So can we draw another rectangle here, 6 meters squared, where these two sides multiply to 6? Well, let's take it easy, 1 and 6. That's our counterexample. So that makes this one false. I've done a lot of talking right now, so let's have you try number 5 right now. So go ahead and pause the video and try number 5 on your own. Now that we're back, let's take a look at number 5 together. Dividing by 2 always produces a number less than the original number. So again, we're trying to find a counterexample. We want to divide by 2. Is there anything we can put on top that would make this statement false? So we want it to say dividing by 2 always produces a number. Can we find one that's more than? Kind of goes back up to what we did here in number 2. If we put a negative up here, we're saying -8 for ease. What's -8 divided by 2? That's -4. Is -4 less than -8? Nope. There's our counterexample. So that is a false statement. This is the end of the notes for section 1. Go ahead and go back through these. If you have any other questions, make sure you're asking if you have any questions, whether it's from Mr. Short or anyone else in the room.